Right, hello and welcome back to another video. This week we're going to be continuing on with what we covered last week, using some different techniques to control where our particles are spawning in our Niagara systems. So if you haven't watched that video, do go and watch that one first, but just as a quick recap, basically we were taking a static mesh that we had vertex painted. If you have a look at the vertex colors here, just a simple black to white gradient, and then doing a little bit of math to animate the values and using that in our spawn module, sampling those vertex colors and then using that to control where our particles are being killed effectively. So anything spawning with less than 0.5 gray would be killed off, and we get this kind of illusion of an animated effect. So a few things. First, we had a question from one of my viewers. Could we change the logic into being a Scratch module? And yes, of course we can. And so if you're doing this kind of thing a lot, maybe you want to set up your own personal sort of module that's going to do this. And we're just going to do that now. So here I've done it already, but if I go to my other example, you can see the logic that we currently have here in Kill Particles. It's a bit messy. There's a few layers of inputs, and so rather than doing it just in a single module, we're going to do it via our own module and make things a little bit cleaner. So I'm just going to double click the Kill Particles module to open it up and use this as a reference. So what's the Kill Particles doing? Well, it's getting the current alive state. It has an input boolean, and then it's just passing through an alive state. So in this case, if we tell it to kill, it's going to kill and overwrite that data alive. So if I go in here and I open up the Scratchpad, and I'm going to make a new Scratch module, and I'm going to call this kill percentage, and recreate the logic that we had last time. So we can kind of see it here actually. We're taking a input mask with black and white value, so just floating value. We're going to take an input percentage, which is our kind of like our threshold for what to keep and what not to keep. And we're also going to expose time as well to allow us to do that animation that we were doing. You could bake it in, but if we expose it, it allows us to sort of give that extra bit of control. We can either choose to animate or not animate, and we'll see that be useful later on. So thinking about how flexible we want to be with this. So so on our input map here, we're going to get the current data instance alive. Is our particle currently alive or not? Get that value, and then also those few floats that I mentioned. So we're going to create a new float, and if I come over here, you can find it. Just F2 or right click rename to give this the correct name. So this is going to be my input mask. Now we could input the vector and then split up in here, or we could keep that outside, and I think it's a bit easier or a bit more useful to keep it outside, because we'll see that sometimes we'll take this input data from a vector 3, sometimes from a vector 2, and by having it only accept floats here and doing the breaking it down outside of the module, it's a bit more flexible. So that's why we're using an input float here. We also want another float that's going to be our threshold. So what percentage of things are we keeping? And then finally another float, which I'm going to call time, or maybe offset, something like that. The name doesn't matter too much. And so what are we doing with this? Well, we are taking our input mask, and I'm going to add time to it. So that's now taking our kind of initial black and white values and just increasing them always over time. Same as we had here, our add float bit of the original logic from last week. We're then going to take a frac of that. Obviously, if we're adding values all the time, it's just going to keep going up. It's not very useful. We need to get those black and white values back, and that's going to give us that kind of effect of a scrolling black and white mask. And then it's just a simple if. So we want to do an if node, and then the way this works is we have to add what we want to compare, and in this case also what we want to pass through. So in this case it's a boolean, and the condition is going to be if this result is greater than this input. think that's the right way around. Let's double check. We'll see if this works. So what are we doing? Well, we've got our scrolling black and white mask, we've got a threshold value, and if our mask value is higher than our threshold value, then we're going to pass through the current alive state, and if not, we're going to kill it. And then I don't want that as a local bool. Let's not do that. I'm going to delete that. Remove pin. The thing I'm going to write to in my output is this same thing here, data instance alive, and that's just telling the Niagara system whether this particle should be alive or not. So taking that kill particle logic, as you can see here, this was just a simple switch based on an input boolean. We've now done the same logic we had before, so rather than based on a single value, it's based on a threshold value. If I apply that, just make sure this works. So here in my kill particles module, I'm just going to remove that. Try and fiddle this around. So we don't going to use this. I'm just going to disable it for now. And instead, I want my kill percentage. That's the one that is here in my Scratch module. And we need to set up some values for this. So I'm just going to set up some defaults that work. So if I go back to my Scratchpad, here we are. Input mask, let's compile. Oh, I need this bit down here. Not really enough screen space for all of this. I wonder if I can move this. Doesn't seem to want to. Try and give myself a bit more room. Here we go. So selecting the input mask, default value of mask I'm going to set to be 1. The default threshold I'm going to set as 0.5, and our default time, that can stay at 0. This was not necessary, that was created by mistake. And I'm going to set the default value of alive to be true as well. So it's going to read that from our particles, but it's also going to take a default of true in here as well. If I reset these to default now, what we should find, if I've done this the right way around, let's just check, maybe it's the wrong way around. If this is greater than this, it should be this way around. There we go. So my mask is 1, my threshold is 0.5, so 1 is always above 0.5, so I'm getting particles everywhere, which is what I expect. But now I can go in and say, well, my input mask, that actually wants to be not a single float value everywhere, but a float from linear color. And if you remember from last week, we are taking our sampled mesh color. So if I type in color over here, if I take my sample static mesh, this is writing a parameter here for mesh color. So I want sample static mesh color, and that value comes into my mask. And I'm just using the red channel. It's all black and white, so it doesn't really matter which channel I'm using. You can see we're only getting our half spiral. If I change my threshold 0, we'll get nothing at all. 1, we'll get the whole thing. 0.2, 0.8. We can control how much of that spiral is visible. If we just do a small amount, and now in time, it's going to change that input to be a actual engine time, and now that's going to keep going up, and we'll get our spiral animating. That's a bit fast. I'm going to multiply that, and I'm going to do time multiplied by, let's say, a quarter, 0.25, just to slow that down. So that's how we could do that using a particular module. So again, up to you how much control you want to add inside the module directly, how much you want to sort of do the logic as Niagara inputs. Maybe that time multiplied by float could be done as a set of inputs, but it also works very quickly if you just multiply those two externally as well. Cool. Let's save this. So that works. That's the same logic we were having last time. But there's a few other things I wanted to look at this time, just sort of to extend that a little bit further. One thing, if we have a look at our sample static mesh, have a look at these parameter rights. So what we used last time was our mesh color, and this was our vertex colors painted in our object. And that's a really powerful way of controlling this. you get full control of your sort of vertex painting. But in this instance, because all we're doing is a linear gradient, we can actually use the mesh UVs themselves. And so our mesh UV is going to give us a red to green or black to white gradient across one channel or one direction, and then another black to white gradient across the other channel as well. So rather than using our make color from, or make float from linear color, if we did make float from vector 2D, plugged in that sampled mesh UV, and then if we look at the Y channel, that's going to give us the exact same result. There's no real difference in terms of what Niagara understands between vertex color data or UV data. It's all just data, it's all just numbers. You can always control it that way as well. And what's quite nice about this is if we take our mesh UVs, let's save this out and then go to the next example. We could have, for example, a textured plane. Now here we've got a kind of black and white rune. Could be a decal, could be a material, could be additive, all of these things. But we only want to spawn our particles where our rune is visible. And that's actually very simple to do. So exact same principle, or exact same approach. Sampling the static mesh. In this case, we're sampling the plane rather than the spiral. And if I just delete these for a second, and you'll see we should get a whole plane, whole square. And then we're using this module here, sample texture. So the sample static mesh is writing to mesh UV, so where about on the plane the particle is spawned. And then we can also sample a texture, and the input UV that we're sampling is the mesh UV that we have sampled already. So we're spawning a particle in the mesh at a certain UV coordinate, and then using that UV coordinate to look up the value in the texture. And because the texture is the same on the mesh and the and inside here in Niagara, we get this kind of connection between the two. And then we're just using that same module we just created for the kill percentage. I'm taking the color data from our sample texture this time instead of our mesh directly, and you can see we're getting our little particles spawning just where our rune is. So one caveat with this, it is only available to GPU sims. If I change that to CPU, the sample texture node only exists on, or only works on GPU sims. This is a performance optimization, I believe. Sampling a texture on the GPU is cheap, doing it on the CPU is very expensive. So that's why this only exists on GPU simulations. But you can see, hopefully, using that same idea of taking some data from somewhere outside of Niagara, or well, inside of Niagara, but driven by something that we've created directly, in this case a texture, and then using that to kill the particles that aren't being useful. And this is great, this works really well, except if we want to animate our material. You might be able to see here in the background, this works because the static texture and the material and the static texture that Niagara understands are the same, no problem. What happens if we start animating our material? Let me just hide my particles for a second. Not the most fancy animation in the world, but hopefully it shows the principle. Obviously you could spend a lot more time on your material timing this all through, but here we just have it sort of slowly rotating. Well, we want to spawn just where our particles are, and there is a way to do this, and this is a little bit more complex and introduces a new system or a new approach. So I'm just going to recreate this one here. Well, actually, what are we doing here? Well, what we're doing is we're sampling the G buffer. What does that mean? Well, if we go up to our buffer visualization and just overview, there's lots of different buffers that make up a frame in Unreal, and we can sample some of them. So we can sample our base color data, and then we can use that data to pass through into our node, our module that we created, with the threshold, with the percentage. And basically we're saying if the screen here is bright, spawn a particle, or keep the particle that has been spawned here alive. If the screen here is dark, so this background, kill that particle. which works really well. And so the way we're going to do this, if we jump over to the content examples, so if you go to the Learn tab of the Epic Games Launcher, there is a content examples pack that has some fantastic examples to do with Niagara, and I happen to have one open here. So this is the Niagara Advanced level, example 1.4. This one here, sample gbuffer attributes, and you can see here our mannequin painted in different colors and also in either metallic or not metallic. And if you look closely at the particles that are spawning, they're actually inheriting the color from the screen or from the object behind, which is a very, very powerful thing to do. You can do all sorts of cool effects with this, and one thing you can do is obviously take that data, pass it through, and use that as a spawn. So let's set that up. So if I open up this example, it gives us a warning saying that this is experimental. Well, that's fine, seems to be stable so far, and I'm sure at some point it will stop being experimental and become a sort of standard feature. Might already be a feature in standard feature in 5, not sure on that. This is 4.26, I believe, but yeah, at one point I'm sure this will become a standard feature. And this isn't a module that just exists, this is actually a Scratch module. So if we double click to open this up, it's a Scratch module. It means it's local to this system, and what we want is to be able to then migrate this or export this to our project, and so we're going to have to save this out as its own thing, and the way we do that is just to take our Scratch module up here, right click and create asset. So a really nice workflow of working locally, test things out. Once you're happy it works, save it out as its own entity in the content browser. So just going to give this a nm for Niagara module, little suffix, make it clear if you want. And what this is doing is it's taking the position of the particle, so where it is in the world, converting that to screen space, and then you have these nodes here: decode base color, decode depth, decode roughness, and metallic. And so that's taking the position in UV space of the particle and then breaking out those different channels, and so we can get access to base color, roughness, and metallic. It's also doing a couple more things. You might see in the inputs, snap particles to sample depth, so you can actually use this to push particles onto your depth buffer, which is going to give you where they are in screen space. We're not going to use that because we're already sampling our plane directly. And then also here, kill particles if too far from sample depth. Well, we're not controlling them, or we're not using the sample depth here, and so we can kind of leave these things out for now. But the important thing here is we're taking the world position of the particle, converting it to screen position, and then getting the sort of screen information to then pass through into colors that we can use. So once this is its own module, if we come back to our content browser, nm sample gbuffer attributes, we can just do a migrate, and this will take that module and any dependents, which in this case there aren't any, and we can just copy it across into our content folder. And there we are. If I come back to my example at the top here, gbuffer, we should have nm Niagara module sample gbuffer attributes. So how do we then use this? Well, if I go back to my example that was working here, ns rune spawn, I'm just going to make a copy. Oops, gbuffer 1, that's fine. Copy this over and set that to be the current one. So this module currently is sampling the mesh, taking the mesh UV data in rights, and then using that to sample a texture, and then killing off our particles based on that texture value. So that works, but it doesn't work as an animated thing. So instead of sampling the texture, I'm just going to delete that. I'm still going to sample the position, but I'm also going to sample, if I take this one off, sample the gbuffer attributes. That's the one I just imported. and we'll see how this works. Turn off the kill percentage, and we should get some particles. Turn off these two as well. You might find that the preview here in Niagara doesn't really work because it doesn't really have a floor. So this depth buffer's gone. You might be able to turn on the floor in the preview scene settings. That might be enough. Or not. But you might need to make sure that you're looking at your viewport window here, just to make sure that we're getting the right data, right information. Okay, so here everything is off. We are sampling the static mesh location of our particles, and they're fitting on the plane. And now we need to sample the gbuffer information. So there's a specific order to this. If we open up our gbuffer here, the input it's taking here is particle position. Well, if I were to just turn this on here, our particles all disappear, because what's happening is our position is being written in the initialize particle module down here. Our particle position, sample static mesh, we're reading it there, we're reading the positions, we're then doing something with it, but we haven't actually moved our particles to the right place yet. So there's a bit of an ordering issue here. So if we sample the static mesh location, then initialize our particles to be at that location, and then when we sample our gbuffer, we should be able to see the results of that. So what's this doing? Gbuffer axis, decode the values, and it's overriding the position. Let's just disable that for now. I'm going to just remove this pin, because we don't want to set where our particles are, we just want to sample the location data. I'm going to remove this pin as well, because we're going to be doing that our own way in a minute. So now we can see our particles are spawning, and we're kind of getting the result that we want, but we're not doing it with our kill percentage here. What's happening is it's taking the color, the base color, and writing that to our particle color. But because our particles are additive, we're getting black particles here, white particles there. If I were to go to the overdraw view mode, he says, you can see we've got particles everywhere. I just select them, that works as well. So we're actually getting particles everywhere. And if I go to my sprite renderer and just change the default sprite material to be opaque, you'll see what we're getting here. So we're getting white particles where we're inheriting the white value on screen, and then black particles where we're inheriting the black values. So you could do it this way, but you're actually paying a cost for all these invisible particles. Just because they are additive with a value of 0, it doesn't mean they're not also giving you some overdraw costs. So rather than doing it purely this way, and you can see we're kind of getting some errors as well here at the screen edge, or sometimes at the plane edge. It's not the best result, not the cleanest. So rather than doing it purely on color, cancel, I can't save over the engine content, that's fine. I'm going to go back to my stack, and I'm going to sample the gbuffer attributes, and then use that data, and then finally I'm going to overwrite the color back to be pure white. And so now we're going to have our particles purely white here, but we've got access to that color data that is correct, that is that white and black, and we're going to use that in our kill percentage. So sample the black and white data, and now here for our mask data, rather than being it is a float from linear color, that is correct, we're going to use the sampled color here, so particles color. So if I just change this to be particles color, take the red channel, keep percentage 50%, and then overwrite the color again at the end. And what we should see is we're only getting particles where we have that white rune happening. And because this is being run on the sort of screen space, it's taking the result of the material. So we're getting particles just here. And if I select the the emitter, you can see from the outline we only have particles here where our rune is visible and animated, which works quite nicely. So, a little bit complex. I will just refresh and go through all of that. So we're sampling our static mesh location. In this case, it's just the basic plane, and that's giving us our mesh position, or our particle position. We're then spawning the particles and initializing using that position. So now our particle position is updated to be correct for the plane that we've imported or that they're spawning on. We're then sampling the G buffer at that location, and in this case we're writing to the color and also the roughness, which we're not using, but we're writing to the color. So we're taking the base color, so those black and white values of the rune as it's animating, because this is all done sort of screen space. We're then killing off any particles that aren't at least 50% white, so all of the black areas disappearing, and then finally we're using this color module to overwrite the color to our particles back to be pure white. So we're not using these sort of additive elements, which works quite well. As a reminder, you won't necessarily see anything correct in here because the depth buffer is not set up correctly, so make sure that you're looking in the world, and you can see we're getting quite a nice result here. A couple of things, or one major thing really, if I just add some gravity to this, and I'm going to do an upwards gravity force. Oh, I've already got one. Let's just make this a little bit stronger, maybe 60 units. You can see our particles spawning off our rune quite nicely. We are getting a few little errors around the edge of the plane. The other inputs here, the snap particles and kill from, that would probably help fix that bit. But the big issue we've got here is this is a screen space effect. So if I look at my particles and then I just bring my camera up, as soon as that goes off screen, they're going to disappear. Don't know how easy that is to see. If I put my gravity up to like something really high, 250, those particles spawning on, coming up nicely, great, looks amazing. Well, looks decent if anyway. As soon as that camera goes off screen, or that plane goes off screen, they're just going to disappear. So there's one disadvantage with this. It is definitely going to be only screen space relative, or it has to be on screen. This example, that's the same one. This example, where we're using the texture sample itself. If I just put that up to something bigger again, this doesn't care. This isn't using screen space. It's calculating those particles even though they're off screen, and getting us the result that we want. So one little note, if you are going to use the G buffer, it's very powerful. You can do some really powerful things, some really cool things, inheriting material information, base color, roughness, etc., all from the screen, but it is only limited to screen. As soon as it's off screen, it's not going to work. Cool. Hopefully that has been helpful and informative. As always, if you've got any questions or you'd like any topics covered in a future tutorial, please do let me know. And a big thanks to all my patrons for supporting the channel, and I will see you all